Welcome to lecture 5 on module 4 of computer organization, in which we will be discussing about the cache memory and its structures and how it will help in increasing the speed of the processor. We know that the processor is operating at very higher speed as compared to the main memory. There is a difference in operation speed compared to the processor and the memory. So if the processor is operating at very high speed, that will indicate how fast the device works. The speed or the speed of a device is measured in terms of the speed of the processor. So the one limitation in order to perform the process faster is that the memory where the programs or the data are stored will not be transferred from the memory to the processor or from the processor to memory as fast as the data is transferred within the registers in case of processors. So the processor has to spend much of its time waiting for the data or the instructions that are to be transferred from the main memory. We know that the programs or the data are stored in the memory from which it will be transferred to the processor. So the processor has to spend much of its time in waiting for the data, waiting to receive the data that is being transferred from the main memory. That is a major drawback in case of achieving a good performance in case of any processor. The speed of the processor depends on how speed the data are transferred between the memory and the main memory and the processor. So it is evident that we cannot increase the speed of the main memory. We cannot increase the speed of the main memory. In order to overcome this, we have, in order to cope up with this, we have a memory called the cache memory. It is an architectural arrangement which makes the main memory appear faster to the processor than it really is. So here, this cache memory is based on the property of a computer program known as locality of reference. This indicates that when a particular program is being executed, the locality of reference indicates that the chances of the program or the code that comes next to it will be executed more oftenly. That means, for example, you have a program at the ith location. You have one program at the ith location. The more chances of executing I plus instruction, there is more chances of executing the I plus 1 instruction as well. The instruction that is present in the I plus 1 location will also has the more chances of getting executed along with the ith instruction. This is called the locality of reference. So when we analyze the programs that are written, we come across one conclusion, that the execution time is spent on the routines in which many instructions are executed repeatedly. That means we know that the program, whatever the program we write, it is a set of routines, or we call it as functions, or a set of programs. So what happens is, in most of the devices, a set of instructions keeps on getting repeated. So when the set of instructions gets repeated, you need to, the processor, the main memory has to transfer those set of instructions multiple times from the main memory to the processor. So what this cache memory will do is, it will understand, or it will analyze the instructions that are being repeatedly executed, and it will place it in a separate location. So many instructions in the localized areas of the program are executed repeatedly during some time period, and the remainder of the program is accessed relatively infrequently. There are the in the program, if you consider, you have two sets of programs or two sets of instructions. One set of instructions that keeps on getting repeatedly executed, whereas one set of instructions are very less frequently used or less frequently accessed by the processor. Together, this is called the locality of reference. So, one set of instruction that gets repeatedly executed is where we need where the cache memory comes into picture. Looking at the set of instructions that keeps on repeating, we are in case of cache memory, we are only concentrating on those set of instructions that keep on repeatedly executing in the program. The set of instructions that keeps on repeatedly executed, on which we are concentrating on. In such cases, that is referred as locality of reference. In case of locality of reference, we have two types of instructions. One is the temporal locality of reference and the spatial locality of reference. The temporal locality of reference indicates that the recently executed instruction is more likely to be executed again very soon. Means we know that this locality of reference indicates that indicates to the set of instructions that are kept repeatedly executed by the processor. So among them we have temporal and the spatial. We have two types, temporal and the spatial. Temporal is the recently executed instruction is likely to be executed again. In case of temporal, it is the instruction that gets executed again. Whereas in case of spatial, the instructions with the address close to the recently executed instructions are likely to be executed. So that means the instructions that are, or the, see, if we have a memory, we know that once the program is written in the higher level language or assembly language, it will be converted into machine language and it will be stored in the memory. So if I consider one statement, there is a if condition, and there are, if you use a if statement, then there are two sets of instruction. One is for true condition, one is for false condition. So out of these two, only one set of instruction, one set of instruction will executed at a time. We know that in all the embedded systems, it is the sequential execution. Sequential execution in the sense, one instruction executes first and the next instruction executes next, and it goes on. So now, if we consider, if you want to consider the spatial locality of reference, here we can consider this if as a temporal. If we consider if as a temporal locality, that means this is the instruction that is being executed repeatedly, that comes under the temporal. Now the more chances of these instruction executes next, right, there is a more chances of these set of instruction that executes next. Here when you compile it and convert it into binary or machine code, machine code, it goes and sits in the memory location. For example, in this set of memory, if the binary equivalent of if is located, then the chances of instructions that are written in these particular locations getting executed is more. The chances of these instructions getting executed is more. These set of instructions, that accompany temporal locality of reference are called as spatial. The locality of reference tells us that a set of instructions that gets repeatedly executed. The locality of reference means that a set of instructions that keeps on repeated. In that instruction, we will have a temporal and the spatial. Temporal indicates to a particular instruction, whereas the spatial indicates to a set of instructions that follow the temporal. Set of instructions that follow temporal. These set of instructions have the chances of executing this set of spatial instruction is more when a temporal gets executed. Now we know that in a program, in whatever the program you write, there are two sets of instructions that are being repeatedly executed. One is temporal and the spatial. So, however, these set of programs are present in the main memory. When a execution takes place, the data has to be transferred from the main memory, maybe a temporal or a spatial, or the data that are less frequently executed. All these data has to be transferred from the main memory to the um, processor. So by changing the architecture we can increase the speed of the processor, or we can reduce the total execution time. We know that the execution time is dependent on the number of instructions that are getting executed. So when the data are transferred from the main memory to processor in a faster rate, the execution time gets reduced. So in order to reduce the execution time, the most frequently used data, the repeated set of what are the instructions that are most frequently repeated, are placed in a separate memory called the cache memory. So what happens is these cache memories uh, will have a blocks of data, blocks in the form of blocks. We know that the processor will not be executing only one instruction at a time. It will be executing multiple instructions or multiple blocks of instructions. So no, in case of, it is not the only one set of instruction or one set of instruction that keeps on repeatedly executed. No, there are many such blocks. So each such repeated blocks, repeated instructions are categorized into the blocks of some size. So these blocks, the spatial aspect suggests that instead of fetching just one item from the main memory to the cache, it is useful to fetch several items that reside at the adjacent address as well. That means, as we have discussed in case of spatial, it is not the particular instruction. It is not the particular instruction that gets repeatedly executed. Instead, this instruction also needs some data supporting data or instructions. When this instruction executes, when this instruction gets executed, the chances of the supporting data getting executed is also more. So instead of copying a single instruction to cache, it is necessary for a designer to copy the entire block into the cache. So this cache line refers to a cache block. The cache line, what we term, is referred to as the cache block. That one set of block that includes temporal and the spatial. So such temporal, there will be many number of such blocks in a cache. So in this slide, we will look into the operation of cache memory. The structure looks like somewhat like this. There will be a processor and there is a main memory. In between a processor and main memory, we have a very fast, uh, very high speed cache memory. So how exactly this works is, in the main memory, you will have the program. You will have a program and the data. So the processor, however, we have discussed how the data are transferred from the processor to main memory and from the main memory to the processor. We have already discussed in the few topics in the first module. Then in the subsequent topics, we have already discussed how the transfer of data takes place between the main memory and the processor. Here, when the data transfers from the main memory to the processor, it goes via the cache memory. Here what happens is, when the data is accessed first time, the cache will analyze the type of data that is being transferred from the main memory to the processor. If it keeps on repeating transferring the data, if it keeps uh, repeating the same instruction being transferred, then it will keep a copy of that in the cache. So next time when the processor requests for the data, same data from the main memory, the cache will supply that to the processor, thereby avoiding the slow process of transferring the same data from the main memory to the processor, thereby reducing the access time, thereby reducing the memory access time. If you reduce the memory access time, automatically the execution time will be reduced. So thus the processor will be faster. So this cache memory helps in speeding up the process of execution in case of processors. So in the cache you will have multiple blocks. For example, you have uh, memory here in case of the main memory. It will copy the block that is being repeatedly executed and paste in the cache. So similarly there will be multiple blocks that are keeps on repeatedly executed by the processor. So all such blocks will be present in the cache. So there is a chances that cache will be filled. In such cases, there is a algorithm called the replacement algorithm. There is something called replacement algorithm which works when the cache is filled. We will look into detail of that replacement algorithm. We will look into the detail of that in the next slide. So here, initially the processor will send the read request to the main memory. The main memory will send the data back to the processor, and that the copy of the data that is being transferred from the memory to the processor is also sent to the cache. And when the next time when the processor requests the same set of data, instead of transferring the data from the main memory, the data will be transferred from the cache memory, thereby reducing the time required to transfer the data from. Since the cache memory is much faster compared to the main memory, the transfer of data takes place between the cache and the processor in very higher speed as compared to the main memory. This is how the cache memory will help in increasing the speed of execution of the instructions. Here in this slide, we will look into the operations of the cache memory. Initially, there will be a read request from the processor, and the words are transferred from the main memory to the cache. This we have discussed in our previous slide. Um, Now, at any given time, only some blocks in the main memory are held in the cache. The entire program that is present in the main memory will not be copied into the cache memory. Instead, only some blocks in the main memory are copied into the cache. So who will decide this? Which blocks in the main memory are in cache? Say the same set of when a copy of we also always specify a copy of main memory. When we refer into the cache memory, we say that a copy that is present in the main memory is pasted into the cache memory. That means the original copy will not be disturbed. Original copy that remains in the main memory itself. Now, which among the blocks of main memory are present in the cache will be determined by a mapping function. There is something called mapping function that determines which are the blocks that are present in the cache. Based on the details of the mapping function, the processor issues read request from the cache. When a cache is full, a block of words need to be transferred from the main memory. Some blocks of words in the cache must be replaced. See, if suppose the cache is full, there is some other instruction that is repeatedly executed compared to the blocks that are already present in the cache, and our cache memory is full. Determine a situation. Imagine a situation when the cache is full and the processor is executing one more set of instructions, or repeatedly executing one more set of instruction. Now in that case, Since the cache is full, you cannot, the main memory cannot place the repeatedly executed instructions directly into the cache. So there should be some block of words that are less frequently used inside the cache that has to be transferred back, or that has to be erased, so that it makes space for the next set of blocks to be copied into the cache. So this is done by the replacement algorithm. So this replacement algorithm is an algorithm that determines which of the blocks can be removed from the cache when the cache is full. So this replacement algorithm will determine which among the blocks that are present in the cache memory can be replaced by the new set of blocks. So in the case of cache memory, when a read process or write process takes place, it will be initiated by the processor. So here the processor does not need to know about the existence of the block that it is going to access, whether it is present in the cache or not. It simply issues the read and write request using the address that refer the main memory. Uh, the processor does not have any idea whether the set of blocks are present in the main memory or in the cache. It just randomly generates a read and write request using the particular address uh, of the memory. So the cache control circuitry determines whether the requested word, there is something called cache control circuitry that determines whether the word is currently exist in the cache or not. If the word that is being accessed by the processor, if it is present in the cache, then the read or write operation is performed on the appropriate cache location. In this case, a read hit or write hit is said to have occurred. So during the read operation, the cache will not be involved. The main memory is not involved during the read operation, since the cache control circuit determines that once determines that the cache is present, the set of data that is being accessed by the processor is present in the cache. During the read operation, the main memory is not involved, whereas during the write operation, both it depends on what type of protocol you are going to use. We have two different types of protocol in case of write hit. During the read hit, during the read hit, main memory is not involved. Main memory is not involved. Whereas when during the write hit, it is write in the sense the processor will write the data back to the memory. So when it writes back to the memory, there are two ways of writing it back to the memory. Either it will write it back only to the cache memory, or since the same copy of the cache block is also present in the main memory, whether it has to be updated or not, that will be decided by the two protocols what we have during the write operation, that is write through protocol and write back or copy back protocol. So during the write through protocol, the cache location and the main memory location are updated simultaneously. For example, the processor will do some calculation, or it may perform some arithmetic operation or logic operation and update the result. During the updation of the result, in case of write through protocol, both the cache memory and the main memory locations are updated simultaneously, because we will be having the same copy in both main memory as well as the cache memory. Same copy of information, the same copy of information will be present in the main memory as well as the cache memory. In the write through protocol, in both these locations, the data will be updated. The result will be updated. Whereas in case of write back or copy back protocol, only the cache location is updated and it is marked as updated with an associated flag bit. often called as dirty or modified bit. So same as the previous, before updating, here in case of write back or copy back protocol, the only the initially the immediate result of the processor is updated only in the cache memory. It will not affect, or it will not be replicated in the main memory. It will be updated uh, only in the cache memory, and it will be associated with the flag bit, and that flag bit is called as the dirty or modified bit. When there is a dirty bit, that indicates that in such instances, when the flag bit, that is the dirty bit, is set during that instant, the data that is present in the cache, a few data that are present in the cache and the main memory will not match. So the main memory location of the word is updated later when the block containing this marked word is removed from the cache. Only when once the cache is full, the more prominent set of blocks will arrive into the cache. During that, the older block has to be removed, or the less frequently used blocks has to be removed by the replacement algorithm, during which the the main memory will be updated if there is a dirty bit present in it. If there is no dirty bit, it right away removes it. If there is a dirty bit set, then it indicates that there is a changes with respect to the data that is present in the cache memory and the main memory. So it has to be updated. The main memory has to be updated. It will be updated before removing that particular block from the cache. This is during the read hit and the write hit. During the read hit, you need not do any changes. You just need to copy the content from the cache into the processor. Whereas during the write operation, you have two process, that is write through protocol and write back protocol. In case of write back, we have the dirty bits. It will update only in the cache memory, whereas the main memory will be updated later. So when a read or write operation takes place, one instance is that whatever the data the processor wants to read or write from particular memory location, that memory location will be present in the cache, one instance. In the other instance, that particular address may not be present in the cache. In such case, uh, such instances are called as cache miss. One is cache hit, one is cache miss. So during the cache miss, when an addressed word is in a read operation, is not in a cache, a read miss occurs. See, now one set of block is not present in the cache, one particular address is not present in the cache, and processor wants to read the data from that particular address. When the processor initiates the read operation, the circuitry that informs or determines whether the block is present in the cache is present or not, it will generate a read miss signal. That means if the data is not present in the cache, then that means that there is a read miss. So what has to be done when the read miss occurs? When read miss occurs, the one way is that the block of words that contain the requested word has to be copied from the main memory into the cache, and from cache it will be forwarded into the processor. The entire block is loaded into the cache and the particular word requested is forwarded to the processor. This is one method. The other method is directly transferring the data from the main memory to the processor, directly from the main memory to the processor, bypassing the cache memory. You need not transfer from memory to cache, from cache to processor. Instead, if the data can be transferred directly from the memory to the processor. This approach is called as the load through or early restart. This approach of called the load through or early restart will avoid the processor's waiting period. See what happens In the conventional method, the memory will transfer the block of data to cache. From cache, it will be transferred to processor. During this time, that it takes time to load the data from the memory to cache and from cache to the processor, right? In order to avoid the processor waiting time, the data can be directly transferred from the memory to the processor. So this reduces the waiting period by using the load through. When a read miss occurs, if you use the concept of load through, then it will reduce the processor's waiting period, but it requires a more complex circuit. As in case of read miss occurs when the addressed word is not present in the cache. Similarly, if a processor wants to write some data, write some result back into the cache memory, if that particular address is not present in the cache, such state is called as write miss. In such conditions, a write miss occurs. Write miss occurs when the addressed word to which the data has to be written is not present in the cache memory. Then in such instances, we have the write through protocol can be used. We know that the write through protocol is the data is transferred directly to the cache memory, or copy of data is sent to the cache memory as well as main memory. If the addressed word is not present in the cache memory, it directly copied to the main memory. It will not be copied to the cache memory. This is write through protocol in case of cache miss, in case of write miss. Whereas in case of regular write operation or write hit, you can update the data both in cache memory as well as main memory by using the write through protocol. There are four states in case of cache, that is read hit and write hit. Read hit and write hit are the conditions when the addressed word is present in the cache. Then we have read miss and the write miss. Read miss and write miss occurs when the addressed word is not present in the cache memory. So based on that, when there is a write miss, we have to use the write through protocol. In case of write through protocol, it will update the result in both cache memory as well as main memory. Since in case of write miss, the address location is not present in the cache memory, it will automatically load the data directly into the main memory. This is about the cache memories.